Okay, welcome to this new video. And in this video, we are going to solve this seemingly tough problem, but which in fact is really easy if you just know a simple like theorem or something like that. And there's an image of like Nepali classroom. I asked AI to like generate a typical Nepali classroom, and the AI generated that. Note that there's a spelling error, so I can't blame AI for that because yeah, AI is just in the training mode. Okay, now how do we solve this problem? So one of the approach might be, let's say, you just want to differentiate like z with respect to x, like, right, assuming y as constant, and you might use quotient rule, right? Again, to find this also you might use quotient rule. You might assume x as constant and find the derivative and then add it, but that will be super tough, right? You can imagine how hard that would be to this to do this. Now another thing is there's actually a theorem which will say us that this will just be uh, I guess 1 over 20 times just z. There's a theorem that directly gives us this answer. Now, about theorem, like how do you go about guessing the theorem, right? Like, you cannot directly just like yo yeah, like, and the theorem can be derived. In fact, first of all, notice that uh, this z is actually homogeneous equation because now what's homogeneous? Homogeneous basically means that degree of all the terms should be same. Now over here, in numerator also the equation is homogeneous. Denominator also the equation is homogeneous, right? Because they have same degrees. Now if two like expressions are homogeneous, like their quotient is also homogeneous. Now basically the rigorous mathematical definition of homogeneous function for two variables is for f of x y, for f of x comma y, if f of tx comma ty is just t to the power n times f of xy, then the equation is said to be homogeneous, right? Now how this works is, so let's say I'll just give you an example. So let's say we are creating an equation. Let's say x square plus xy plus y square. Over here, basically, this has degree 2, this has degree 2. This also has 1, 1. So they are in product, so that will get added, and that's also 2. So all have same degrees, right? Now, if you just try to find out tx, ty, so definitely here we will have t square x square, and again, here will be 2 t's. So just the same as degrees, so there will be 2 t square xy plus t square y square, right? Now you can take t square common, this will just be x square plus xy plus y square, and this was just the f of xy, right? So this is how this definition works. And the benefit of having this definition is, so this definition will help us categorize. Like, I mean, in the case of fractions, we cannot really see, I mean, there's just not a single expression, right? There are two expressions. So for the fractions, if you wanna like categorize if this expression is homogeneous or not, we will need this definition. We will need this definition to check it. So first of all, if you wanna check this, if it's homogeneous or not, so yeah, first of all, let us say that this g is just a function of x and y, which is x to the power 1 by 4 plus y to the power 1 by 4 divided by x to the power 1 by 5 plus y to the power 1 by 5, right? Now if you substitute, tx and ty, this will just be tx to the power 1 by 4 plus ty to the power 1 by 4 divided by tx to the power 1 by 5 plus ty to the power 1 by 5, right? Now you can just take these common, so t to the power 1 by 4, x to the power 1 by 4 minus y to the power 1 by 4 divided by t to the power 1 by 5, x to the power 1 by 5, this is plus y to the power 1 by 5. Now you can just like take use the law of exponents, so this will be 1 by 4 minus 1 by 5, x to the power 1 by 4 plus y to the power 1 by 4 divided by x to the power 1 by 5 plus y to the power 1 by 5, right? So this will just be t to the power 1 by 20, and we know that this is just f of xy, right? So we showed that this f of tx comma ty is equal to t to the power n times f of xy, and this thing over here, so if this is in the form, if this is in exactly this form, then this n that we see over here will be our degrees. So degree of this expression is just 1 over 20. So in this case, if you want to find it, it's in a shortcut way. So what we can also do is to find the degree. Like first of all, find the degree of numerator and degree of denominator and subtract them. So that's basically the same thing, the 1 by 20. So this is our degree, right? And yeah, so we also proved that it's homogeneous. We also found out its degree, right? Okay, now for homogeneous function, like there's actually a standard theorem to find this. Now let's try to find it and let's try to see. Okay, so first of all, now we know that if like in this case g is a function of x and y, and that's homogeneous, right? Now let's consider a general f of xy. That's homogeneous. That's homogeneous, right? And we just learned that homogeneous function f of tx comma ty will just be t to the power n times f of xy, right? Now, what we will try to do is we will try to differentiate both sides with respect to t, because because yeah, like that I because you know that, like, if you try to do that, this will just be n times t to the power n minus 1, and again you can make it as n by t times t to the power n f of xy. So this is the same thing, and having got the same thing, we can use that and make some manipulations to get some results. So that's why I'm doing this, because the same thing is repeated, and repetition is almost always beautiful. So partial differentiation with respect to t in both sides. So now in this side basically is a function of tx and ty, right? This one is basically a function of tx and ty, and again each of these is again a function of t, right? So what you have to do is, so a small change in t can increase tx, which can again increase f. Again, a small change in t can increase ty, which can again increase f. So if I want to differentiate this with respect to t, so we should consider this both cases. So the rate of change in f caused due to change in tx due to t, right? Also, the rate of change in f caused due to ty due to change in t, right? So this is our partial differentiation of f with respect to t. Now for this side, since this has no t, this is just as same as constant. So if we differentiate the other side, should be n t to the power n minus 1 times f of xy, right? Now if you try to evaluate this, now, a partial differentiation of tx with respect to t, that's the same as normal differentiation. So that will just be x, right? And partial f by partial tx plus this will just be y, right? So partial f by, I mean, this is just y, part y times this will be uh, partial f by partial ty. And now over here, this will just be n. I can take by t in over here into to the power n times f of xy. And the benefit is we can take it back to our previous expression, like this one. And this is the same as f of tx comma ty, right? So this is just n by t times f of tx comma ty, right? So over here, what we have got is, now guys also know that this f is actually a function of tx comma ty in this case while we are differentiating. This was function of tx comma ty while we were differentiating, right? We need to know that actually, like, what was like there, because yeah, because only in that case like this thing is true, because if it was just x and y, that wouldn't have been true, right? So we need to know that. Okay, so now if we know this, so let me write this down in proper format now. So x times partial f of tx comma ty by partial tx plus y times partial f of tx comma ty by partial ty will just be n by t times f of tx comma ty, right? Now guys, now let us just say that tx is equals to u, ty is equal to b. Okay, so if you say that over here that x will be u by t, now this is partial f of u comma b with respect to u, plus this will just be b by t, right? Partial f of u comma b by partial of b is equals to n by t f of u comma b, right? Now we can just like see that we can just cancel these t's. So obviously the t is not zero, so we can just cancel these t's. Now this is just u partial f u b or partial u plus b partial f u b by partial b is equals to n f times u b. Alright? Now these u b are just dummy variables, so I can replace them by any other variable. So I can just now again substitute u as x, b as y, so that will give me x times partial of f of x comma y by partial x plus y times partial f of x comma y by partial y, so is equals to n times f of xy. So yeah, we saw that. Now in this way we saw that if f is a function of x and y, and this is also a what do you call that, homogeneous function, if this is also homogeneous function, then this is true. X times partial f by partial x, where f is function of x and y, and y times partial f by partial y, where f is function of x and y, is equals to n times f, where f is function of x and y. So we saw that that's true, right? In our case, g is also a function of exactly x and y, right? G is a function of x and y, right? And the degree is just our n in this case is just, we found out that's just 1 by 20, right? So that will be x times partial g by partial x plus y times partial g by partial y will just be 1 by 20 times this is just g itself. So that's our answer. So this is just g by 20, and that's a really elegant answer. So I guess hope you guys enjoyed this video. Now, whenever you have homogeneous function, notice that you, and if there's exactly this same equation, no, nothing any different. Yeah, if there's same equation, and if you have homogeneous equation, you can directly use this theorem, right? And yeah, hope this is helpful in some ways. I don't know, maybe. And yeah, look forward to seeing you in the upcoming videos.